So, this is the lecture on adaptive learning rate. We have already discussed various types of feed forward network, and the training that we have used is based on gradient descent technique, where the learning rate eta is a fixed quantity. In this class, we will talk about what is the purpose of making this learning rate adaptive, how we can achieve it. So, subjects to be covered in this class are motivation for adaptive learning rate, Lyapunov stability theory. We have already discussed about stability theory. This is just to familiarize you in this class, so that you can appreciate how to derive this adaptive learning rate using Lyapunov stability function, using Lyapunov function, and then some simulations and discussion. So, it is a feed forward network. This feed forward network can be a multi-layer network or RBFN network. There is various architecture of feed forward network. It can be a multi-layered network, it can be a radial basis function network. And once you have this kind of structure, the goal is to identify this W which is the weight vector. What we have done is that we have taken all these weights in the first layer, second layer, and as many layers we have in the network, and then put them in a vector format, which is W. That means, the total number of weights in this network is capital M. The training data consists of, say, n patterns, okay, xp and yp. xp is the vector here, and that is the input vector, and yp is the output vector. Not necessarily that we have only single output or two input. This is simply a schematic diagram. The network can have as many inputs and as many outputs, and of course, as many hidden units. The update law for such multi-layer network, radial basis function network, has this structure, where W t plus 1 is W 2 minus eta del E upon del W, where eta is the learning rate, and this is a gradient descent. Del E by del W is the gradient descent, that is, E is the cost function, which is I should say error cost function, and that is minimized by this update rule. Now, let us look at the motivation for adaptive learning rate. In general, if I am looking at a function f x, which is of y equal to f x, let us say. So, this is my f x and this is x, and when f is nonlinear, then the usual curve can look like this. This is just a representative, this need not be exact. In principle, what this curve says is that this curve has many, this is one minimum, this is another minimum, this is another minimum. So, in this curve there are three minimums, out of which two are local minimum and this is global minimum. But there can be another function f x for which there can be many local minimum and many global minimum. So, many local minima and many global minima. So, these are the normal characteristic of a nonlinear function f x if I plot with respect to x. The objective is find x such that y is minimum, find x such that y is minimum. So, the objective is how I reach here, not here, starting from any initial condition. So, if you see, if I use a gradient descent rule and if I start from this point, this red circle, and then from here I glide down and come here, this point. Okay. But if I can change this initial position to this point, then I can come here by using the rule x new is x old minus eta del y by del x. So, this is my normal principle of gradient descent, that I can come to the local minimum which is nearest to the starting initial point, but such weight update does not guarantee that I can reach here. Of course, in this case you can easily see that if I am starting from here, if I increase my learning rate step, that eta, then this initial position may go to this position by simply changing this eta a bigger value, and then by lowering eta I can easily reach this. We have discussed these things in previous classes. So, with adaptive learning rate one can employ a higher learning rate when the error is far from global minimum and a smaller learning rate when it is near to it. But how do you know it? So, there are certain heuristic methods people have tried, but today we would like to give a comprehensive approach how to compute this adaptive eta, such that even if I start from initial weight which is nearer to a local minimum, still I can reach the global minimum. That is the objective. So, the objective is to achieve global convergence for a non-quadratic, non-convex, nonlinear function without increasing the computational complexity. In gradient descent, learning rate is fixed. If one can have a larger learning rate for a point far away from a global minimum and a smaller learning rate for a point closer to the global minimum, then it would be possible to avoid local minima and ensure global convergence. This necessitates the need of adaptive learning rate. Today in this class we will derive the how to comprehensively compute eta, the adaptive learning rate, such that we reach, of course, our algorithm does not guarantee that we will have a global convergence, but it is better than gradient descent. So, and we will be using Lyapunov function. What is a Lyapunov function? For a system that is defined in the state space x t, V x is a Lyapunov function if it is positive definite, and it grows that is V x t increases as x t increases. So, the once we have selected such a Lyapunov function, and if I compute the rate derivative of that Lyapunov function v dot x, if it is negative definite, then the system is asymptotically stable. This is the Lyapunov function. Another condition is that if v dot becomes 0, then x t also converges to 0. Okay. So, weight update law using Lyapunov based approach. Now, normally given a network which is characterized by W, the network we have already discussed all these things, a network it is characterized by weight vector W, and the input vector is x p, then network output is y p hat. This is network prediction. P stands for pattern. I have n such patterns. So, the usual quadratic function is given for this kind of network for training the weight vector W is y p, which is desired one, y hat p is the actual one. So, y p is desired, y hat p is predicted by the network. So, you can see that this is a usual quadratic function that we have already discussed. So, this is for n patterns, and if I have also multiple output, then I can put another index here and make a sum there. Now, for such a network, let us choose a Lyapunov function candidate for the system as below. V is half y tilde transpose y tilde. So, it implies that here I have this y tilde is actually the error at for the pattern 1, y tilde is a vector of error function, the error that occurs when a network predicts given some input x p with specific w. So, this is error for the pattern 1, error for pattern p and error for pattern n. So, and we take this error, that is we have p sets of n sets of capital N sets of patterns. For each pattern we compute the error, and each error is an element of y vector y tilde. So, obviously V is, so you can easily see this whatever I am writing here and this E is same. So, in this case V is same as E, we have just written in a vector format. So, this expression has been written in a vector format in V, and we say okay, let this be a Lyapunov function, okay. And then I try to differentiate V dot. So, you check here, this is my Lyapunov function, and in this there is a term called y hat p, and this y hat p is a w. So, the objective is that how can I find out w dot. So, the objective is find w dot such that V dot is negative definite. This is the objective. Okay. So, find w dot such that V dot, if I differentiate V, that such that V dot is negative definite. Okay. That is how we deal with a nonlinear function. You can easily see this is a nonlinear dynamics, because V is a nonlinear function and y hat p is a function of w, nonlinear function, and I am now saying w dot, that is the evolution of w follows certain law, certain dynamic law. So, then this becomes a completely dynamic equation, and if V dot can be negative definite, then I can say the w dot that is given to me is a weight update law that guarantees stability. Okay. The time derivative of Lyapunov function V is given now, V dot is, see you see that V was half y transpose tilde y, the scalar function, y is a vector. So, if I differentiate this, and where y tilde is the vector of all the errors for each pattern. So, V dot is minus y tilde del y hat by del w, w dot. You can easily see here, if I differentiate this V dot, okay. So, y tilde and then differentiation of this quantity with respect to w, and then w dot gives rise to, I can write this equation as minus y tilde transpose j w dot. So, you can easily see that this I hope this expression is clear to you, where I simply differentiate this V, this negative sign comes because y tilde is y actual minus y hat. So, when I differentiate that, I get minus del y hat by del w, this term, and w dot. So, the relation that I have added is dV by dt is dV by dW into dW by dt. Okay. So, that is what W dot is dW by dt, and this particular expression, this part, you can easily say that this is a vector and this is a this is another vector, but this is a row vector. So, in this J, of course, y we can always say this is a vector, sorry, y is a vector, W is another vector. So, obviously, this one is a matrix actually, which is this. So, I define this quantity as J, and J equal to del y upon del W, this quantity, and this is a this matrix is n into m, the dimension, because W has m dimension, capital M, and y has dimension n. So, I hope now you understood what is V dot. V dot is this quantity. Now, the theorem is, if W is updated by this equation, the W t dash is W naught plus 0 to t dash W dot dt. So, at every time t, I compute this relationship where this W dot is given by this expression, okay, which is a little probably you are not so familiar, but y tilde, this is norm square. Norm square means y tilde is a vector. So, you take each element, square it, add them, and take the root of that, that is a norm. So, if you do not take a root, norm square. So, W dot is this norm square, again another is J transpose y tilde is another vector, again norm square, plus this epsilon is a small positive constant, and then J transpose y tilde. If this is the case, this is W dot, then y tilde converges to 0 under the condition that W dot exists along the convergence trajectory. So, that is what we need. We need that this y tilde, the vector y tilde should converge to a 0 vector under the condition that W dot exists along the convergence trajectory. Okay. So, this is the theorem. Once we have a theorem, we must prove that theorem. So, how do we prove it? Okay, this theorem, we will talk this theorem as Lyapunov function 1, because we prove it using Lyapunov theory, Lyapunov function concept. So, what we do, we take this equation 6 and we replace this in 4 and compute V dot. If you do that, we get V dot to be y tilde square and this quantity. So, you can easily see that this quantity is always either positive, this you take the negative, the other quantity, this is a positive quantity, this is another positive quantity, this is also another positive quantity. So, hence this quantity is always either negative, because the negative sign is there, or 0, okay. And that assures us if this quantity will go to 0, sorry, if V 1 dot goes to 0, then this quantity also will go to 0, okay. If V 1 dot is uniformly continuous and bounded, then as t tends to infinity, V 1 dot tends to 0. If V 1 dot will tends to 0, you can easily see that y tilde will go to 0. That is the proof. Objective is that the objective was that our error cost function, which is simply y tilde transpose y tilde half, okay, this quantity. So, if y tilde goes to 0, then cost function becomes 0. Okay. So, that is the function is minimized. So, the weight update law is a Bayes update law that we discussed now. The instantaneous LF1 learning algorithm can be derived as, for instantaneous what we do, we do not take the vector y tilde, we simply take a scalar. Y tilde is simply y minus y p. This is no more a vector, this is for instantaneous quantity. So, w dot is this quantity. If I consider what is should be the weight update law for instantaneous update, we have already discussed earlier, there is batch update, there is instantaneous update. For batch update we consider all the patterns, for instantaneous update we consider the recent pattern, current pattern. So, then this becomes the update law using the same Lyapunov function approach. And if I look at this w dot, how will I update this? If I take a discrete equivalent of this equation, then this is the discrete equivalent, the difference equation form of the continuous update law, which is w hat t plus 1 is w hat t plus mu w dot t. Okay, this is how the weight update is done, where mu is a suitable small constant, such that this equation approximates equation 8. Okay. So, we derived a weight update law w dot that would ensure that y tilde converges to 0 if w dot exists along the convergence trajectory. That was our theorem and we proved it. Now, let us see, let us go in depth of this algorithm. So, if you look at the BP algorithm, back propagation algorithm, delta w is minus eta del E upon del w. What is delta w? Now, I always write w t plus 1 is w t plus delta w, right. So, this delta w, as you can see, this is a gradient descent law, okay, gradient descent method, and this gradient descent method can be written as eta j I transpose y tilde, where this j I is same as the j I is del y I by del w. You can easily see this is j I. J I is del y by del w. Okay. This is a row vector. This is a row vector because y is a scalar. So, okay, this is no I there. So, del y hat by del w is j I. So, if I write the equation, this equation is same as this equation, this eta j I transpose y tilde is same as minus eta del E upon del w. So, then I write this equation, and using the recent algorithm which I called LF1, we got a equation which is w t plus 1 is w t plus mu y tilde norm square by j I transpose y tilde norm square into j I transpose y tilde. So, you can easily see this back propagation algorithm that was very popular, and the algorithm we have derived, this has a remarkable same identity, except that eta is replaced, where in back propagation this eta is a fixed quantity, and in this adaptive this Lyapunov function based weight update law that we just now derived is this quantity, whereas this quantity is a time dependent quantity. This is a time dependent quantity. So, that gives us a notion that using Lyapunov function we can actually derive a adaptive learning rate, which is eta. So, comparing above two equations, we find that the fixed learning rate eta in BP algorithm is replaced by its adaptive version, which is eta adaptive. Okay. So, this is the first time, actually this is our own work, the first time we derived an adaptive learning rate using comprehensively we found this an expression for adaptive learning rate using Lyapunov function method. So, the convergence of LF1 is that we said that y tilde converges to 0 we showed, but there was a condition that if W dot converges along the W dot exists along the convergence trajectory, then our theorem is right, but W dot may not exist along the convergence trajectory, then our thing is does not hold good. So, that the theorem states that global convergence of LF1 is guaranteed provided W dot exists along the convergence trajectory. This in turn necessitates that del V1 by del W is the norm of that is Z transpose Y tilde is not equal to 0. So, you can easily see that it says that this says the W dot exists along the convergence trajectory, and for this existing convergence trajectory, meaning that this should be a this should always exist, J transpose Y tilde should always exist. So, this implies that J transpose Y tilde should not be 0, or del V1 by upon del W is 0, indicates a local minimum of the error function. The theorem only says that global minimum is reached only when local minima are avoided during the training. Since instantaneous update rule introduces noise, it may be possible to reach global minimum in some cases. However, global convergence is not guaranteed. So, this is the implication of the theorem that W dot exists along the convergence trajectory. So, this is the second version of that same algorithm, where our Lyapunov function V2 is the earlier Lyapunov function. This was the earlier Lyapunov function we took, and we added a term which is lambda into W dot transpose W dot. This term was added into the error function V2. So, again if we follow the same method, we find out V2 dot, then this can be written in this form, which is minus Y tilde transpose J minus D W dot, where J is del Y upon del W and D is this quantity, that is lambda 1 upon Y tilde norm square Y tilde W double dot transpose. So, if I put this, then this V2 dot which is computed here, this is V2, this is V2 dot, and this is same quantity as this. Now, we propose another theorem. If the update law for weight vector W follows the dynamics given by the following nonlinear differential equation, which is 14, where this alpha W is have the form this, that is Y tilde norm square upon J transpose Y tilde norm square plus epsilon is a scalar function of weight vector W, and epsilon is a small positive constant, then Y tilde converges to 0 under the condition that J minus D transpose Y tilde is non-zero along the convergence trajectory. So, this should be a non-zero along the convergence trajectory. So, we take this W dot, and this W dot can be written in this form now. This from here I can write this equation in this form, and substituting for W dot from this equation, if I replace this W dot here, which is V2 dot, then V2 dot becomes this quantity, and you can easily see that this is a positive quantity or 0, this is again a positive quantity, this is another positive quantity or 0. So, in that sense if you can look at that this, since J minus D transpose y tilde is non-zero, V 2 dot is less than 0 for all y tilde less than equal to 0, and V 2 dot is 0 if y tilde equal to 0. If V 2 dot is uniformly continuous and bounded, then according to Berberlet's lemma, as t tends to infinity, V 2 dot tends to 0, implying y tilde will converge to 0, which was the theorem. So, the theorem is proved that y tilde will again converge to 0 provided the condition, which is the condition is J minus D transpose y tilde is non-zero along the convergence trajectory. This is necessary because if this is not 0, if this becomes 0, then W dot does not get updated. We say that W dot should exist. For W dot existing here, this quantity should not become 0. If this becomes 0, then obviously W dot becomes 0, then weight cannot move along. Okay? The trajectory of weight update becomes stagnant, you can't have further. So, this should not become 0. If this becomes 0, then this theorem does not hold good, and this can be 0 in local minima, that is for LF1, and for LF2 we showed now the same thing, that this quantity also should not become 0. As long as this is not 0, then y tilde will converge to 0. So, that is we derived two Lyapunov function based algorithm, but in this both the theorems we showed that y tilde will converge to 0, but there is a condition. In the first one the condition was that J I transpose y tilde should not become 0, and here J minus D transpose y tilde should not become 0, and these conditions, because of this condition the global convergence is not achieved. Okay. But anyway, the weight update law that we talked about, the difference equation version of that equation, that weight update law is this particular format, which is equation 17, and this can be written in terms of two form. You see, W t plus 1 is W t, and there is some quantity here which is a time varying quantity, then J transpose P y tilde, and here this is the instantaneous. Okay, that is why P has come, P for each pattern, and minus again this is another quantity. Okay. Whereas mu 1 is mu plus lambda, and that quantity is written again another time varying quantity into W double dot. So, this is a gradient term, with some input, and this is W double dot into some constant. So, where W double dot is computed using this formula, which you can derive using Euler's method. If I use the same cost function and apply back propagation, I get this equation. Okay. And the recursive term is this, the equation 18, and now also we are getting the same thing, but we are now getting eta dash and mu dash are time varying quantity, that is a adaptive quantity using Lyapunov function. So, that is Lyapunov function, the method that we have described gives us weight update law, which is similar to gradient descent, but that but is very important, because where the learning rate associated is adaptive now. Okay. So, this term normally in back propagation we say acceleration term, but our mu dash is a adaptive acceleration term, and eta dash in back propagation is a fixed learning rate, whereas in our case it is a adaptive learning rate. Of course, I will not go in details of this, because this requires a little bit of more introspection and you really need to understand go details about it. Simple a classroom teaching will not help you to understand this unless you really. So, I would rather means this particular class I am just telling you, or I am giving you, or I am delivering this lecture just to let you know or to inspire you to think about the methodology that will help you to get a better convergence algorithm. Okay. Anyway, the most important this convergence of LF2 is again the same thing, that this should not become 0. Okay. And if this does not become 0, then it ensures global convergence, but we cannot guarantee that this cannot become 0. So, this can become 0, you can easily see that J transpose Y tilde is D transpose Y tilde. Okay. So, if this is the case, then the solution of above equation represent local minima, and this is 0, this is a local equation, local minima it reaches. Okay. So, we talked about here that this should exist, that means this should not become 0 for global convergence. Okay. But W dot vanishes whenever this is 0. So, if we assume J is not equal to D, then rank of J minus D equal to N ensures global convergence. Okay. Because if J is not equal to D, that implies this is 0 only when Y tilde is 0, that is global convergence. At global convergence Y tilde is 0. The other condition is that when J transpose Y tilde, but this case of course is for when this is true, the solution of the above equation represents local minimum, and then the convergence is not global. Since for a neural network n is much less than m, so there are at least m minus n vectors for which solution do not exist, and hence local minima do not occur. Increasing number of hidden layers or hidden neurons, chances of encountering local minima can be reduced because of this particular statement. Increasing the number of output neurons increases both m and n as well as n by m. Thus, for MIMO system there are more local minima as compared to single output system. So, more complexity, more local minima. But one of the interesting part, I will not go in details here, all that I will tell that using Lyapunov function, the second Lyapunov function LF2 algorithm, the first one is LF1, second one is LF2. Using LF2 one can show that acceleration term that we are adding, because of that most of the time, because whenever this quantity this del V1 upon del W is 0, that does not ensure that W double dot. So, whenever del V1 by del W is 0 does not imply that W double dot is 0, and this fact actually ensures that this term can actually drive away this local minima, it can bring the weight from this local minima and it can come here. So, that is we can avoid local minimum, not always, but in some cases using LF2 algorithm by adding that extra term which is half W dot transpose into W. That extra term helps us because that introduces an acceleration term in our learning algorithm. That acceleration term can take away the weight from being stuck in the local minima towards the global minima. So, now we talked about adaptive learning rate. What is this adaptive learning rate? Now, let us consider the LF1 algorithm, and in this algorithm, if we apply this algorithm to a XOR function, all of you know what is an XOR function, that when both input are equal, then the output is 0, and unequal the output is 1. Okay. So, that is XOR function. We have 4 patterns in XOR function for 2 input XOR function, okay. 4 patterns for a 2 input XOR function. So, that is I have this, okay, this is XOR x1, x2 and y. And if I train this function, if I train a network to learn this function, then when I plot this eta function, you see for each pattern I have 4 curves here, 1, 2, 3 and 4, and you can easily see this eta is increasing and decreasing and until it goes to 0. So, what you are seeing is that 2 important things: learning rate is not fixed, which in BP it is a fixed quantity, and learning rate goes to 0 as error goes to 0, okay, which is important. So, that is what is important, that how the learning should be done. Learning should be done in the beginning, eta should be very high or whatever is necessary, but as the learning is over, that for the patterns the network has already learnt, then the eta should be 0, y eta should be there, but for back propagation the eta is always fixed, all right. So, this is the this is important, that what is the meaning of adaptive learning rate. It has 2 important property: eta is time varying, and it has a property that as y tilde converges to 0, eta also becomes 0. So, simulation results now we will talk about. So, this is your LF1 versus LF2 XOR function. So, let me first summarize. We got 2 weight update, we got we proposed 2 theorem for weight update in a feed forward network. It can be a multi-layered network, it can be a radial basis function network, and we said that this weight update algorithm will ensure y tilde to converge to 0, that is global convergence, provided 2 conditions, each there is a condition for each theorem that has to be satisfied. In one case, that while the weights are sliding along the convergence trajectory, they should not be stuck in the local minima. This is the first theorem. Second theorem, it says J minus D transpose J minus D into transpose y, that also should not be 0. Okay. Again, the solution also, that solution also ensures us to be in local minimum if it becomes 0. So, now the problem is which is better, LF1 or LF2. We gave some idea that LF2 can avoid local minimum, okay. But let us do simulation and see whatever theory we predicted, whether that is true or wrong. So, you see that the first one, what we have done here for XOR function, we took a feed forward neural network, that is a multi-layered neural network, and using that neural network, what we did, we started from this different initial conditions W, and for every run we wanted to see how many training epochs were necessary for each algorithm for convergence. So, if you look at the top one, which are the broken line, that represents the number of training epoch. One epoch is 4 training over 4 patterns, okay. XOR function, I have minus 1 is minus 1, minus 1 plus 1 is plus 1. So, this is my x 1, this is my x 2, this is my y, and plus 1 minus 1 is plus 1, plus 1 plus 1 is minus 1. This is my XOR function. And if I train this XOR function in a multilayer network using my Lyapunov function 1 algorithm, then from every different initial condition, because initial weights are all random. So, for each initial condition I get, you see that these are the number of patterns here and one epoch is this 4 patterns, that I give these 4 patterns to my network, train it, okay. And again I repeat it. So, like that, if I train almost like here it is almost near 200 and here is around 120 or so, and it is varying, okay, it is varying. Sometime also it goes up to 300, and you can easily see the number of training epochs necessary to train a XOR function using LF1, that number of epochs are always a varying quantity, and there is a good deal of fluctuation, that is almost as 120 training epochs to 300 training epochs. Whereas, if you look at LF2, that is almost constant, you see that this is a straight line except these fluctuations here, there is one fluctuation, there is another fluctuation, but otherwise they are very fixed quantity, and this is always below the training epochs that are necessary using LF1. So, the observation is LF2 provides tangible improvement over LF1 both in terms of convergence time and training epochs, and most important is that it is invariant to initial condition. Okay. You have to recognize training a neural network means you start from a new initial condition. Each initial condition will lead to a different convergence time. If that is the case, then the algorithm is not a good one. So, can I say that I have an algorithm that ensures that whatever may be my initial weight vector, my convergence time is independent of that, all right, that is important. So, that was for XOR function, and this is for 3-bit parity problem, and in 3-bit parity problem you can easily see, I hope that you can get all these functions in many textbooks, they are there, XOR function 3-bit parity. So, if you take a 3-bit parity function, again you can see that LF1 is again very fluctuating, very much fluctuating, in almost like 750 epoch to almost like 3000 epoch, it fluctuates. Whereas, the LF2, the number of training epochs are fixed almost at 500 level, it is almost fixed. Very rarely it is here one fluctuation, second fluctuation here, big fluctuation, and 3. So, mostly you see again LF2 performs better than LF1 both in terms of computation time and training epochs. Okay. So, this is a 2D Gabor function, and for this Gabor function the LF1 and LF2, if you look at the error, RMS error, and this is the iterations, okay, training iterations. So, you can easily see that LF2 the error is much less, it has a lesser value than the LF1. So, it has a better convergence performance. This we have a kind of table format. We have compared the results of for performance of backpropagation algorithm and LF1 and LF2 for a XOR function, and you can easily see that number of epochs that are necessary for training a XOR function using eta equal to 0.5 is 5620, eta equal to 0.95 3769, whereas In case of LF1 we take only 165 and LF2 only 120, and if you if a epoch simply gives the number of time I have to train, but what is the total computation time? If you look at that, because of course one can argue that gradient descent is a very simple function, the computationally very simple, but if you look at the total number of computation time in second that is necessary, if you again see that also, in that case the proposed algorithm are much better, because it is 0.0038 whereas the back propagation is 0.0354. So, it is pretty fast, at least 10 times faster than the back propagation algorithm in convergence time. 3-bit parity problem, again you can easily see here LF2 takes 738 number of epochs and LF1 is 1338 epochs, whereas the back propagation takes pretty long time, 5941 with eta 0.95, eta 0.5, 12032 and so forth. And computation time also you look at LF2 is 0.0676 second, whereas the back propagation takes 0.483 second for training. So, this is a 3-bit parity problem we talked about. 8x3 encoder, you already know what is encoder. So, if I use a 8x3 encoder map using a neural network, feed forward neural network, again if you look at the number of epochs that are necessary, LF2 and LF1 using Lyapunov function, they are pretty small compared to back propagation, and also time wise also you can see the comparison. The 2D Gabor function that we took a multi-layer network with 40 hidden unit, 80 hidden unit, and we trained using back propagation network as well as LF1 and LF2 only 40. So, you can see that RMS error per run, we ran the we trained the network using many initial conditions, weight conditions, and averaged it over say 100 such runs, and then we computed average error, and you can easily see the comparison is in terms of RMS error, LF1 and LF2 are much better than the back propagation algorithm. Okay. So, now let us come to the final part, the global convergence of Lyapunov based learning algorithm. It is possible if we take the objective function, this V2 Lyapunov function is mu V1 plus half sigma this square, where V1 is this quantity, which is the Lyapunov function we have considered for our first network, first theorem. And if I compute V2 dot, then this becomes like this 22. So, the objective is to select and weight update lot W dot such that the global minimum B1 equal to 0 and del B1 by del W equal to 0 is simultaneously reached. That is, you see that if I have a cost function, then at this del B1 by del W also 0 and V1 this quantity is also 0 here. So, in this case if you look at here this is 0, del V1 by del W is 0, but V1 is not 0 here, V1 is 0 here, sorry. So, let me now try to explain you what is, how can we, what is meaning of attaining a global convergence. If I look at the Lyapunov function, which is now V2, so you can easily see that if this is my Lyapunov function, where at this point B1 is 0 and at this point this quantity del V1 by del W also 0. So, V2 is 0 here in this point. but in this case this one is 0, but this is not 0 in this case. In this case this one is 0, but this is not 0. So, if I can take a Lyapunov function like this, some researchers have proved that we can attain the global convergence, but what is the problem? If I take this 22 as a Lyapunov this as a Lyapunov function which is 21, then I have to make sure that this V 2 dot is negative definite, and for that you see that this is my weight update law. The researchers have shown it, but unfortunately this involves a Hessian matrix and its inversion. So, computationally it is impossible. Imagine what is that normally a neural network will have number of weights at least in hundreds, okay, in a tangible application it is in number of 100, I mean it is at least 100. So, if in that case you can easily see that this is a very huge matrix whose inversion is very difficult. I am not it is not difficult to compute the inversion, but time consuming. So, obviously they cannot be applied online, but the algorithm that we presented today is applicable online. Okay. So, implementation of weight update algorithm becomes very difficult due to the presence of a Hessian term, inverse presence of the inverse of the Hessian term. So, the above algorithm is of only theoretical interest, okay. And also this weight update algorithm is similar to BP learning algorithm with a fixed learning rate, whereas the learning rate that we presented today is adaptive. So, Lyapunov function algorithm performs better than I did not talk about today what is extended Kalman filtering. So, it is not necessary. Is performs better in comparison to back propagation algorithm in terms of speed and accuracy. LF2, the second algorithm that we propose today, is avoids local minima to a greater extent as compared to LF1. It is seen that by choosing a proper network architecture it is possible to reach global minimum. LF1 algorithm has an interesting parallel, both LF1 and LF2 has an interesting parallel with the conventional BP algorithm, where the fixed learning rate of BP is replaced by adaptive learning rate. So, conclusion is that adaptive learning rate can be comprehensively computed using Lyapunov function approach. So, here we select and we select a Lyapunov function V and then find V dot, propose W dot such that V dot is negative definite. By doing this, what we did is that we attained a adaptive learning rate, that is in gradient descent we have W t plus 1 is W t plus eta del E by del W, and this is gradient descent, and in Lyapunov function we got the same plus eta adaptive del E by del W. So, Lyapunov function we derived an adaptive eta, okay, otherwise the structure is same. So, I hope that this is clear for you how to compute comprehensively an adaptive learning rate such that our convergence is better, although the two algorithms that we propose does not guarantee again global convergence, but it gives us an idea how we can certainly improve the convergence of such algorithm for feed forward networks. Thank you.